Assalamu alaikum everybody. So let's proceed with the chapter 24. Okay, and let me quickly remind you what we have done so far in this chapter. And sorry for the quality of the projection, but we will try to manage inshallah. Okay. So at the beginning of the chapter, we introduced the work done by an electric force, WE, you can see. We said the work done by the electrostatic force is the integral of f of E dotted with ds. Okay, and since the electrostatic force is QE, we can write this is equal to QE dotted with ds. Okay, we introduced the concept of electric potential energy, and we said the difference in electric potential energy is actually equal minus the work done by the electrostatic force, and so this is okay, so this is minus QE dotted with ds. Okay, and we also introduced the potential, and we said the potential is just the electric potential energy divided by Q. So we also defined delta V, and we said this is delta U divided by Q, so this is equal to minus E dotted with ds. Okay, and we also said now that we have defined the difference in potential energy, we can include it in the conservation of energy equation that you had in physics 121, and we said the total work done by external forces on a system is equal delta K, the change in kinetic energy, plus the change in gravitational potential energy, plus the change in electric potential energy, plus the change in thermal energy, and so on. And we said usually in the problems that we'll be doing in this course, we will not consider friction, so this is 0. In most cases, if you are using, for example, electrons and protons, the gravitation force is negligible compared to the electrostatic force, so we will also ignore the change in potential energy due to gravitational force. Okay, so this is conservation. And if the system, there is no external forces acting on the system, obviously the external work is going to be 0. So if no external forces, W external is equal to 0, hence we can write delta K plus delta U is equal to 0. Okay, last time we also were able to determine what is the potential due to a point charge. So if we have a point charge Q and we are at the distance R at point P, we determined that Vp is equal to K Q divided by the distance R. Okay, so we said this is a scalar quantity that can be positive or negative depending on the charge. If the charge is positive, the potential due to that positive charge is positive. If the charge is negative, the potential is negative. And we said if the superposition principle applies to this, so if you have a number of point charges, you can determine at a certain point the potential from each of these charges and add them, scalar addition. Okay, any questions so far? All right, so let's proceed to the next topic. And again, I'm sorry about the quality of the projection. Let me see if I can improve it. Yeah, a little bit better. Okay, so maybe let's see if I go to the presentation mode if it's better. Let's maybe a little bit better. Okay, let's assume we have charges Q1, Q2, Q3, and we want to determine the electric potential energy of the three fixed point charges. So these charges, they apply forces on one another. So if you release the charges, either they will move. So there is a stored potential energy, and we want to determine what is the potential energy of these charges. Okay, so we will assume, in order to do this, we know from the conservation of energy principle, the work done by external forces. Oops. Okay, the work done by external forces is delta K plus delta U here, delta U electric. Okay, if delta K is equal to 0, for example, if we move a charge from one location to another, the initial velocity is 0 and the final velocity is 0, delta K is 0, so we can write the external work done by this force, external force, is just equal, since delta K is 0, is just equal to the change in electric potential energy. Yeah, I don't know why he has a camera there. Okay, thank you for telling me. I will okay, so let me move it to another place. Okay, so we said, yeah, here actually the conservation of energy equation, we said that, the work done by external force is equal delta K plus delta U electric. And so if we assume that the charge has an initial zero velocity and the final zero velocity, so K initially is 0, K final is 0, delta K is going to be equal to 0. So this term goes to 0, that means the external work is just equal the change in potential energy. Okay, and we will try to determine it if we bring these charges from infinity. So at infinity, remember we said the potential energy at infinity is 0, so let's try to bring them from infinity to this configuration. They are close to each other. Okay, so delta U is U final minus U initial. U initial is U at infinity, which is usually we take to be 0. Okay, so we can determine that in order to determine the potential energy of these charges, we have to determine how much work needs to be done in order to bring them from infinity to this configuration. So in order to determine the potential energy of a system of charges, we can determine how much work is done by an external force to bring them from infinity to this configuration, and that will be U. And that's what we will do. So this is a rule. The electric potential energy of a system of fixed point charges is equal to the work that must be done by an external agent to assemble the system by bringing each point charge from an infinite distance. Oh, so this is just the same thing. All right, so let's do it step by step. Okay, so this is what we want to do. So what we are going to do, we're going to bring the first charge. We will bring Q1 from infinity. Okay, so Q1 is coming from infinity to this position. Q1 is not moving in an electric field, so the work done to bring it from infinity to this position is 0, because there is no opposing electric field that is helping it or opposing it. So, or let's say we are starting at Q1, there is no work done. So since there is no external field when Q1 is moving, so the work applied to bring the charge Q1 from infinity is equal to 0. Okay, now we will bring the second charge. When we bring the second charge, there is already an electric field due to Q1, so we cannot ignore. So there will be either a repulsive force or an attractive force, depending on whether the charges are same sign or opposite sign. So if they are same sign, they will repel each other, so we will be doing work against the electrostatic force. But if the two charges are opposite, positive and negative, there is an attractive force, so the work that we'll be doing, we will be helped by this electrostatic force. Okay, so we're bringing Q2 from infinity to a distance R12. Okay, and remember we said the work applied, is just equal to delta U. This is external work, is delta U. Okay, So, and we can write this as Q delta V, Q delta V. So since V at infinity is 0, so we're bringing this from Q final, V final, minus 0, and V final we have already done this, so this is going to be equal to, remember V final is KQ1, so this is Q2, Q1, Q1 divided by R. So we will end up with KQ1, Q2 divided by R. So this is the work that needs to be done in order to bring a charge Q2 from infinity. So this is what we are doing here. Okay, so Q2 times delta V, which is Q2 times V final minus V initial. V initial is 0. Okay, so we end up with this is the equation, that this is the work that has to be done in order to bring a charge Q2 from infinity close to Q1 at a distance R1, 2. So this is now, this is the potential energy of the charge Q1 and Q2 when they are at a distance R1, 2. And we said in order to do the potential energy, first of all we do the work that is necessary to bring the charges from infinity. But we are not done, we still have another charge Q3. So let's bring Q3 and do the same thing. So this is the first term, okay, K Q1 Q2 divided by the distance. Okay, so this is, let's call it U12, or the potential energy of charge 1 and 2, U12. Now we're going to bring a charge Q3 from infinity. So we have Q1 and Q2 are already there. We're going to bring charge Q3 from infinity. Okay, and so we can do the same thing. We can determine how much work is necessary to bring it from infinity. Okay, and so we can write, okay, so the work for the work applied to bring charge 3 is going to be, we can do the same thing, Q3 times V at this point, let's call it this point P here, at point P, which is so what's the potential at point P? We have to do the potential from Q1 and the potential from Q2. So this is going to be Q3. The potential from Q1 is K Q1 divided by the distance. So this is R1, 3. Okay. The potential due to Q2 is going to be K Q2 divided by the distance. So this is R1, 3. This is R2, 3. So R2, 3. So notice this now is equal K Q1 Q3 divided by R1, 3 plus K Q2 Q3 divided by R2, 3. This is how much work we need to do in order to bring a charge Q3 from infinity to this position. Please pay attention with me here. Okay, so now we can add all of the works. So we did work to bring charge Q2, then we did work to bring charge Q3. We add all of them, that will give us all the work that needs to be done to bring the charges from infinity. Okay, so this is what we just have done. Okay, so let's call them U13 and U23. Okay, so now if we add all the works done by the external forces to bring the charges, it's going to be equal U12 plus U13 plus U23. So it's actually the sum of the potential energy between charge 1 and 2 plus the potential energy between charge 1 and 3 plus the potential energy between charge 2 and 3. So this is now this is U12, U13 and U23. So now this is actually the potential energy of these charges when they are at this configuration, at the configuration that we have shown here. Okay, so we can expand this. If you bring a fourth charge from infinity, you do the same thing. You determine how much work is needed to bring the fourth charge. Okay, and then you end up with many more terms. So let's so if we have a fourth charge, okay, so what we will do, first of all, we have the potential energy to bring a charge 2 close to charge 1, that's U12. So now we have 1 and 2, you can bring 3. When you bring 3, you have to add the potential energy between 1 and 3 and 2 and 3. Okay? Then when you bring charge 4 from infinity, you have to add now the potential energy between charge 1 and 4, 2 and 4, and 3 and 4. And you add all of these, you will get the total potential energy of this system of 4 charges. Okay? So these are the applied works. And now if you add them, this is what you obtain. So U12 plus U13 plus U14 plus U23 plus U24 plus U34. Okay? So we can write this in a general form. So we can write as a summation. Okay? So let's use the notation Uij is the potential energy to bring charge I and J close to each other. So it's KQi times Qj divided by the distance between them. And now we can write a general equation. The potential energy to bring n charges together is equal to the summation for I going to 1 to n and j going from I plus 1 to n, Qi, Qj, Rij. So you can verify that this will give you this if, for example, n is equal to 4. So this is a general equation. Usually we don't ask you to do 4 or 5. We usually will stop at 2 or 3. But you should be able to determine. So the potential energy to bring 2 charges from infinity to a certain distance is the potential energy U12, which is K, Q1, Q2 divided by the distance between them. The distance, not the distance squared. Okay? If you bring a third charge, you use U12 plus U13 plus U23. So you will have 3 elements or 3 contributions of potential energies. Okay? All right, so let's do this checkpoint. And so let me end the show and I'll start the Kahoot. Discard. Okay, so let me go here and duplicate chapter 24, play, start. Okay, so please enter the Kahoot, everybody, so that you will be marked present. So it's 166 4856, 166 4856. Let me put the question, so while you're joining. Okay. So let me read it for you since the font is not very clear on the screen. Okay, the figure, yeah, you can barely see it. This is charge Q1 and Q2, a distance R12 between them. Take Q2 to be negative source charge, so Q2 is a negative source charge, and Q1 to be a second charge whose sign can be changed. If Q1 is initially positive, so and is changed to a charge of the same magnitude but negative, so Q1 is changed from a positive charge to a negative charge. What happens to the potential at the position of Q1 due to Q2? So again, this is Q1, this is Q2. Q2 is a negative charge, source charge. Q2 is a negative source charge, this one. Okay, Q1 can be positive or negative. So the question here is what happens to the potential at Q1, at this point here, at point P, when we change the charge from positive to negative. Clear? Question is clear? Yeah. Okay, so I'll give you 10 or 15 seconds. Think about it. So will it increase? Will it decrease? Will it remain the same? نعم؟ مش سمعتك شو؟ The pen? Oh, the pen. 1664856. I said the pen. The pen. 1664856. Sorry. I don't know if it's my hearing or it's your voice is low. I'm starting to doubt my ears. Maybe I should go check. Okay, so next. Okay, 5 seconds remaining. Okay, so we have whoa, 12 correct answers and 18 incorrect answers. Okay, so this is a tricky question. Okay, what is the potential due to charge Q2 at a point P? And this is point P. The potential is, no, I asked for the potential, not the potential energy. I did not ask for the potential energy of Q1 and Q2. I said, what is the potential at due to Q2 at this point P? So it's K Q2, this is divided by the distance R12. Does this depend on Q1? No, it does not depend on Q1. Remember, we said the potential is only dependent on the source charge. It's dependent on the electric field. It does not depend on the charge that you put there. It can be negative, positive, small or large charge. The potential is only dependent on the source charge that is causing the electric field, and hence the potential at that point. Okay, واضح? So this is a tricky question because it's asking not about potential energy. You have to keep these things different, separate. There is potential energy of a system, and there is the potential due to a charge or a charge distribution. Next question. And you kind of expect what will be the next question. All right, so here 53531 is leading by a short margin. Okay, so this is the next question. In the figure, take Q2 be negative source charge and Q1 to be the second charge whose sign can be changed. Okay, when Q1 is changed from positive to negative, so we're changing it from positive to negative, what happens to the potential energy of the two charge system? What happens to the potential energy of the two charge system? Will it increase, decrease, or remain the same? Okay, so I'll give you a few seconds to think about it. You can write it down on your paper. What do you think will happen to the potential energy of the two charge system if we change one of them? Remember, Q2 is negative, Q1 is changed from positive to negative. Okay, it changes from positive to negative. So you need to write this down or to write the equations. Okay, can we start? Ready? Okay, so let me go next. Ten seconds. Oh, 14 correct and 14 and 17 incorrect. First of all, I have one that is saying D. There was no. Okay, all right. Then last time I had one question had A, B, C, and two answered D. Yeah, so I hope by mistake. Okay, so clearly this question is also confusing because you can see, and so let's go and see what's happening here. All right, so let's in these questions I have to write the equations. Okay, so let's start. So we have the charge Q2 is negative, okay, and Q1 is the second charge. Q1 is initially positive, so let's do U12. Oh, this is the previous question. Yeah, sorry. Yeah, this is the next question. Okay, all right, thank you. All right, so let's do U12 initially. So we know the equation is K Q1 Q2 divided by the distance between them. Okay, so Q2 is negative and Q1 is negative. Negative times negative, it will give you positive. So this is positive. Okay, so now we change the charge Q1 to become negative. Sorry, we changed from positive. We changed from positive to negative. Sorry. So Q1 is positive and Q2 is negative. So the product is negative. Okay, we change Q1 to negative. So now U12 prime is going to be K Q1 Q2 divided by R12, but now it is going to be positively, and negative times negative is positive. So did the potential energy increase or decrease? It increased. It went from negative to positive. So you see here the signs are very important. The signs of the source charge and the test charge. Well, here it's potential energy, so we should not speak about source, and we should speak about the system of the two charges. It's K Q1 Q2 divided by the distance. So the sign of Q1 has an effect. The sign of Q2 has an effect. So you cannot ignore. There is no absolute values here. Unlike the magnitude of the force, we used for the magnitude of the force, we just used K Q1 Q2 divided by the distance squared. So we did not care in that situation about the signs. We determined the magnitude, and then we use our reasoning to determine whether the forces are repulsive or attractive forces. Okay? So yes?
When the charge changes, does the R changes also?
No. The charge are at the same position. So R1 and 2 is not changing here. If the R12 changes, then obviously the potential energy will change. Okay? So let's do this problem. Here we have a figure that shows a charge Q1 that is 2 microcoulombs that is located at the origin. So this is charge Q1 at the origin. Okay? And charge Q2 is negative. It's minus 6 microcoulombs, and it's located at 0.3 meters. At 0.3 meters. So it's along the y-axis. So this is charge Q2 here. Find the total electric potential due to these charges at point P. So this is point P here. Point P is at 4 meters along the x-axis. So this is simple. Vp is equal to the potential due to Q1. Potential due to Q1. So let me call this R1. Let me call this R2. And let me call this D. The distance between Q2 and point P. Okay. So the potential at point P due to Q1 is equal K Q1 divided by the distance, which is R1. Okay. The potential due to Q2 is equal to what? K Q2. What's the distance? D. The distance is D. So don't confuse. So the distance here is D, and D is going to, if you calculate D, square root of 0.3 squared, 3 squared, 3 squared plus 4 squared is just 5 meters. Okay, so you can calculate this. Obviously, since Q1 is positive, this term is positive, Q2 is negative, this term is negative. So when you add them, you should get, so you should not forget about the sign, you get minus 6.29 10 to the power 3, minus 6.29 10 to the power 3 volts. Okay, this is question A. Question B, find the change in potential energy of the system of the two charges plus a third charge Q3. So this is a third charge Q3 as the latter charge moves from infinity to point P. It moves, we're moving it from infinity to point P. We want to determine what is the potential energy of the system. Okay, so this is now the new configuration. Okay, so we can write the potential energy of the system. We can write this is equal to U12 plus U13 plus U23. Okay, so this is going to be K Q1 Q2 divided by the distance between them, and we called it R2. Okay, that's 3 meters, plus 1 and 3, this is plus K Q1 Q3 divided by the distance between them, that's what we called R1, and it's 4 meters. Then we have to add plus K Now we have Q2 and Q3. K Q2, Q3, okay, divided by the distance between them. We said it's D. Okay, so this is now, oh, here they're asking for the change in potential energy, not the potential energy. So this is the final potential energy. What is the initial potential energy? The initial potential energy, we only had two charges, 1 and 2. So we can write it, it's the two charges, yes, U1, 2. Okay, so this is, your initial is actually K, Q1, Q2, divided by the distance between them, which we called R2. Now delta U is U final minus U initial, and when you do that, so let me do it here. Okay, so let me okay, so basically this term will cancel, and we will end up with only, so this will be equal to K Q1 Q3 divided by R1 plus K Q2 Q3 divided by D. So we did, what is the final configuration? What is the potential energy of the final configuration? What is the potential energy of the initial configuration? And we take the difference, U final minus U initial. It will give us the change, because they are asking, this is a little bit tricky, the change in potential energy. They did not ask for the potential energy. A different way of doing this, I can just determine how much work is done to bring the charge, the third charge, from infinity to this location. So I can do the following. So let me add slide. Okay. Okay. So we had charge, I think this one Q1, Q2, and we brought Q3. Okay. I can determine what is the potential due to 1 and 2. We already have done that. We said this is K Q1 over R1. We call this R1, this R2, and this is D. Okay, and plus Q2 divided by D. This is a potential. The work done to bring the third charge, this is external work, remember, is going to be equal, we can write delta U, or we can write it, it's Q delta V. Okay, or so here, since we're bringing it from infinity, and at infinity it's 0, so this is going to be equal QV, and this is Q3, and we replace V by this one, we obtain that this is Q3, or K Q1 Q3, K Q1 Q3 divided by R1 plus K Q2 Q3 divided by D. The same equation as the one we found earlier. This is the same equation. To tell you the truth, I am much more confident with doing the initial potential energy, final potential energy, and do delta U. I know the other one is simpler, it's just determining the work and it's QV, but I like this one because you will see when we do problem solving, this is much better. Okay, any question about potential energy of the system of charges? So the potential due to a charge is KQ divided by the distance at a certain point. If you bring two charges at a certain distance, the potential energy, electric potential energy of these two charges is K Q1 Q2 divided by the distance between them. Keep those separate. One is potential and one is potential energy. Okay, all right, let me okay, so let me quickly introduce this concept, and we will come back to it next week. Okay, and let me go to the presentation mode. Okay. Okay, so here let's assume you have an electric field and you want to determine, you want to calculate the component of this electric field along a certain direction S. So let's write, for example, this is a direction S. I want to determine what's the component of the electric field along that direction. So we can do a projection of this perpendicular projection, and we can determine the component of this. But we have a nice mathematical equation to do that. Okay, it's minus the partial derivative of the potential if we have an equation for the potential due to this electric field. So remember, a charge or a charge distribution creates an electric field and also creates a potential. So if we have an equation for the potential, I can just take the partial derivative of that potential with respect of this direction S. So this is a general equation. Remember before we said V is minus the integral of E dotted with ds. So here, when we go from E to V, we do the integral or minus the integral, and when we go from V to E, we do the derivative. So one we take the derivative and one so this is, but we have to clarify this is along a direction S. Okay, this is a partial derivative. You have seen partial derivative in calculus. Good. Okay, so the component of the electric field in any direction is the negative of the rate of change of the electric potential with distance in that direction, or it's minus the partial derivative of the potential along that direction, minus dv ds. So let's, since we usually use Cartesian coordinates x and y and z, okay, we can write this, that the component of the electric field along the x direction is minus the derivative of the potential with respect to the x direction, minus dv dx. Similarly, the component of the electric field along the y direction is minus dv dy, and the component of the electric field along the z direction is minus dv dz. Okay, so let me stop here. I want to solve some problems. We will come back to this next week. Discard. Okay, and let me start another Kahoot. Okay, and at the same time I want to stop the Panapto recording, so I will start another one. Stop.